Have you ever found yourself looking at, the incredible breakthroughs in AI and data science, things like personalized recommendations or complex medical diagnostics,
Mhm.
and wondered how on earth do they actually do that? It often feels a bit like magic, doesn't it?
It really does.
But behind that magic, turning these huge mountains of raw data into, well, profound insights or powerful predictions, there's this robust, incredibly well-developed ecosystem of Python
Right.
libraries.
It's the plumbing, in a way.
Exactly. And today on the deep dive, we're not just going to scratch the surface. We're going to dive deep into 5 foundational Python libraries: NumPy, Pandas, Matplotlib, Seaborn, and Scikit-learn.
The big five, really.
Yeah, but our mission isn't about writing code, not exactly. It's more about understanding the fundamental why they were designed the way they were, their kind of fascinating historical journeys, and crucially, how they seamlessly interlock, how they work together to form the very backbone of modern data science and machine learning.
Exactly. Our aim here is to give you a conceptual, sort of big picture understanding. As we explore each one, you'll start to see that these libraries aren't just a random collection of tools.
Right.
They form a truly layered architecture.
Right.
Each piece is meticulously engineered to solve very specific, often quite intricate challenges.
Mm.
And grasping this interplay, understanding why one library hands off data to another is absolutely crucial. It helps you make informed decisions in your own data work. And honestly, it just deepens your appreciation for the elegant engineering that underpins so much of what we do.
Yeah, you start seeing the thought behind it all.
Precisely. We'll even touch on the fundamental differences in how data is represented. Think about the contrast between NumPy's incredibly efficient homogeneous arrays versus Panda's more flexible labeled structures.
Okay.
These differences are really key to understanding their distinct strengths and why they're both, in their own way, completely indispensable.
Yeah. All right, let's unpack this then. Our first stop, NumPy. If you've ever heard the phrase bedrock in data science, well, it's almost certainly referring to NumPy.
Absolutely. It is the fundamental package powering scientific computing in Python, no question.
So what's its core purpose? What was it built to do?
Its core purpose is actually remarkably focused, almost deceptively simple. It's to introduce an efficient n-dimensional array, what NumPy calls the end array, and to provide a suite of incredibly fast, vectorized mathematical functions that operate on these arrays.
Okay, end array. But you might be thinking, hang on, Python already has lists. Why do I need this special array?
And that's a fantastic question, because standard Python itself, pure Python, isn't optimized for heavy numerical calculation.
Right. It's flexible, but not fast for math.
Exactly. Pure Python loops, especially if you're looping over large data sets, can be agonizingly slow. So NumPy steps in. It overcomes this limitation by performing all those complex mathematical operations like adding two huge arrays together or calculating the sign of millions of numbers. It does all that in highly optimized C and Fortran code.
Ah, so it's happening under the hood, so to speak.
Totally under the hood. You write Python code, but the heavy lifting, the number crunching, is done in these super fast compiled languages.
It reminds me of driving a high-performance car. Python, the language, that's like the sleek dashboard and the user-friendly interface, the steering wheel, the pedals, everything you touch directly. But beneath that, hidden away, is the super efficient, finely tuned calculation engine, specifically built for intense numerical tasks at scale, almost like a Formula One engine. That's NumPy.
That's a great analogy.
It allows the Python language to achieve incredible speed for array-based computing, the kind of speed you'd maybe expect from tools like MATLAB.
Right. And the key to this efficiency, it really is the underarray itself. This underarray isn't just any old list. It's a homogeneously typed, contiguous memory block.
Okay, unpack those terms. Homogeneously typed.
It means every single element within a NumPy array must be of the exact same data type. So if it's an array of integers, every element is an integer. If it's floats, they're all floats. No mixing allowed within one array.
And contiguous memory block.
That means all those elements, because they're the same type and size, can be stored right next to each other in the computer's memory, in one unbroken sequence.
Ah, okay. And why is that homogeneity so important?
Because that homogeneity enables the contiguous memory allocation. Storing everything together minimizes overhead and makes accessing the data significantly faster. Imagine a library where all the sci-fi books are lined up perfectly, spine to spine.
Easy to find the one you want.
Exactly. Compare that to a library where sci-fi, history, and romance novels are all jumbled together on the same shelf. Finding that specific sci-fi book takes much longer.
So NumPy makes a trade-off.
It's a deliberate, profound trade-off. NumPy sacrifices the flexibility of Python lists, where you can mix numbers and strings or whatever,
Right.
for raw computational performance. And this is absolutely crucial when you're dealing with the truly massive data sets common in scientific computing and machine learning.
So this design choice, the end array, it becomes like a standard.
Absolutely.
Yeah.
It elevates the end array to be the de facto intermediate data representation.
Yeah.
It's the foundational standard for numerical data interchange across the entire Python data science ecosystem. It's the common language that almost all the other libraries will talk about, understand, and use.
That concept of homogeneity and the performance boost it gives, that really feels like the core philosophical win of NumPy. It sort of dictates everything else.
Precisely. It enables what we call vectorized operations, or UFuncs, that stands for universal functions.
Okay, UFuncs, what are they?
These are those optimized C routines we mentioned. They apply operations element-wise across entire arrays without needing explicit Python loops. You can add 2 huge arrays or compute the square root of every element all in one go.
Bypassing the slower Python interpreter for each step.
Exactly. You get sea-level speeds. Then there's broadcasting. This is remarkably powerful, a bit magical sometimes.
Broadcasting, what does that do?
It automatically expands smaller arrays to conform to the shape of larger ones during arithmetic operations.
How does that help?
It lets you do really intuitive things without writing complicated loops. Like, say you want to add the number 5 to every element in a million-element array.
Right.
With broadcasting, you just write myArray plus 5. NumPy figures out how to apply that 5-foot to every element efficiently.
Yeah.
Or you could add a vector, a 1D array, to every row of a matrix, a 2D array, without manually replicating the vector.
Okay. That simplifies the code a lot.
Hugely. And makes it much more efficient under the hood. Beyond basic math, NumPy also packs a comprehensive library for linear algebra matrix multiplication, decompositions, that sort of thing, plus Fourier transforms and random number generation. Often, these interface with highly optimized libraries like BLA and LPAC for maximum performance.
So it leverages existing high-performance code.
Yes, it doesn't reinvent the wheel for everything. And critically, it exposes a C API. Along with support for tools like Python, this allows other Python extensions or even your own custom code to directly manipulate NumPy arrays in C for incredible speed boosts.
Wow.
This makes the end array truly a universal common language for data exchange among performance-critical Python libraries.
So it's not just a collection of tools. It really is the Rosetta Stone for numerical data in Python.
That's fascinating. And the history, how did this all come about? It wasn't just created overnight, was it? No, definitely not. Its origins actually trace way back to the 1990s. There was a matrix SIG, a special interest group, discussing the need for numeric array support in Python. Even Guido van Rossum, Python's creator, was involved in those early discussions.
Really? So the need was recognized very early on?
Oh, yeah. This led to a library called Numeric, created by Jim Hugunin in the late 90s. It was really the first proper implementation of Python's array object.
Okay, numeric.
Then a bit later, another library called NumArray emerged. It had some improvements, especially for handling larger arrays. But by the early 2000s, this fragmentation...
Having 2 competing libraries.
Exactly. It became a real headache for the growing scientific Python community. Imagine trying to build a house when you have 2 different types of screwdrivers that only work on certain screws. It slowed things down.
So how did they solve that?
Well, here's where it gets really interesting. In 2005, a developer named Travis Oliphant took on the absolutely monumental task of unifying numeric and NumArray.
Wow, that sounds like a huge job.
It was. He essentially incorporated the best features of NumArray back into numeric, did extensive modifications, and released the result as NumPy 1.0 in 2006.
So NumPy was born from merging these 2 earlier efforts.
Pretty much. And interestingly, it actually started as a component within the broader SciPy project.
Oh, I thought it was always separate.
Not initially, but it was a stroke of genius, really, to separate it out. That way, users could install just the core array tools NumPy without needing the entire much larger SciPy stack, which included more specialized scientific algorithms.
That makes sense. It lowers the barrier to entry.
Definitely. And that certainly helped with its broader adoption and allowed it to grow independently.
And it hasn't stopped evolving since 2006. Right.
Not at all. NumPy continues to be this vibrant, community-driven open-source project. It's now fiscally supported by NumFosi Hess, which is a nonprofit dedicated to nurturing open-source scientific computing tools.
Like a foundation supporting it.
Exactly. And as of 2025, it's already on version 2.x, with continuous improvements being made showing how it adapts to new scientific demands and hardware. Its role as a pillar of scientific programming in Python is just indisputable.
It underpins so many other libraries.
It's foundational for Pandas, Matplotlib, SciPy itself, Scikit-learn,
Yeah.
and even the newer big machine learning frameworks like TensorFlow and PyTorch were heavily inspired by NumPy's API design.
The influence is huge.
And the sheer numbers tell the story. It sees hundreds of millions of downloads every single month.
Wow. Hundreds of millions.
Yeah. That's a testament to how utterly indispensable it is across both academia and industry for any serious numerical work in Python.
So going back to the architecture for a second, you mentioned the end array has the data and metadata separate.
That's right. Conceptually, you can think of the end array as having two key parts. There's the raw data buffer that's the actual block of contiguous memory holding the numbers.
Okay.
And then there's the metadata. This is like the instruction manual for the data buffer. It tells NumPy the data type, D-type, the shape of the array, how many dimensions and how long each is, and the strides, how many bytes to jump in memory to get to the next element along each dimension.
Strides.
Yeah.
Okay, that sounds a bit technical.
It is, but it's brilliant. Because this separation allows for incredibly flexible array usage without needing to duplicate the actual data.
How so?
Well, imagine you have a huge matrix, millions of numbers. If you want to just look at a small slice of it, or if you want to transpose it, swap rows and columns, NumPy can often achieve that just by creating new metadata that points to the same original data buffer, but interprets it differently with a different shape or different strides.
Ah, so it doesn't have to copy all those millions of numbers.
Exactly. It just creates a new view onto the existing data. This saves a ton of memory and computational effort, especially for large data sets. It's truly a testament to thoughtful, efficient engineering.
That makes so much sense. So when we talk about where NumPy is used, its use cases, it sounds like it's pretty much everywhere numerical data is involved.
Almost. It's involved in virtually every stage where numerical data needs efficient handling, particularly in data preparation and the actual computation stages. Think scientific computing and simulation.
Like physics or engineering.
Absolutely. Researchers use NumPy for everything from solving complex differential equations to processing experimental data from particle accelerators or climate models, signal processing, image analysis. It's fundamental.
Okay. And in data analysis itself, before machine learning.
Definitely. For data analysis and feature engineering, NumPy arrays are often the underlying structure for computations. Cleaning data, transforming features, maybe you need to normalize a matrix of features so they're all on the same scale, or compute statistical measures like mean and standard deviation across an entire data set. Pandas often uses NumPy for these calculations internally.
Right. And then in machine learning and AI.
Well, while higher-level libraries like Scikit-learn provide the algorithms, NumPy provides the essential language they speak tensors and matrices. Scikit-learn, for instance, expects its input data, your features X and target Y, as NumPy arrays.
So it's the input format.
Primarily, yes.
Yeah.
And as we mentioned, the big deep learning frameworks like TensorFlow and PyTorch were directly inspired by NumPy's lend array design. They have their own tensor structures, often optimized for GPUs, but the API feels very familiar if you know NumPy. And you often use NumPy for pre-processing data before feeding it into those deep learning models, too.
It seems indispensable. Are there any really surprising or maybe famous examples of where NumPy played a key role?
Oh, absolutely. What's truly remarkable is NumPy's direct role in some of the most groundbreaking scientific achievements recently. It was instrumental in processing the immense data sets that led to the first image of a black hole.
Wow, really? How?
That incredible image wasn't just taken by a single camera, right? It was computationally reconstructed from petabytes of data collected by radio telescopes around the world. The algorithms used for that reconstruction rely heavily on incredibly efficient array operations, fast Fourier transforms, matrix manipulations, the kind of things NumPy excels at.
So NumPy made that computation feasible.
It was a critical piece of the puzzle, yeah. The same applies to the detection of gravitational waves by LIGO and Virgo. Extracting those incredibly faint signals from noisy detector data required sophisticated signal processing, again heavily reliant on fast numerical computations, powered by libraries like NumPy and SciPy.
That's amazing. It's not just abstract math. It's enabling discovery.
Exactly. You also find it heavily used in image processing. Libraries like OpenCV, which are standard for computer vision tasks, represent images as NumPy arrays essentially, 2D or 3D arrays of pixel values. This allows for incredibly fast pixel-wise operations, filtering, transformations, and so on. These examples really hammer home how its abstract numerical capabilities translate into tangible, world-changing outcomes.
Okay, so summing up NumPy's strengths. Biggest one seems obvious. Performance.
Performance and efficiency on numeric data, hands down. It's orders of magnitude faster than pure Python for numerical loops. That's because of those contiguous memory arrays and the vectorized operations running in optimized C and Fortran.
Right. Decades of optimization packed in.
Exactly. Its API, built around the AND array and those universal functions, ufuncs, is also remarkably simple and consistent, which makes it stable and relatively easy to learn the basics. Plus, it's incredibly well documented.
And it acts as that unifying standard we talked about.
Yes, its adoption across so many other libraries is a huge strength. Once you understand NumPy arrays, you can interact with countless other tools, Pandas, Scikit-learn, Matplotlib seamlessly. Data just flows between them. It also handles a broad range of numeric data types and array shapes, from 1D vectors to high-dimensional tensors, and includes basic support for missing values via special NaN, not a number, placeholders. It's truly a battle-tested foundation.
But like any tool, it must have limitations, right? Where does NumPy fall short or maybe deliberately stop?
Absolutely. And these limitations are mostly by design, it's important to understand. NumPy is intentionally a low-level toolkit, meaning it deliberately lacks some higher-level data handling capabilities. For example, it doesn't have labeled axes, like column names in a spreadsheet or named index rows. That's the domain of Pandas.
Okay, no labels. What else?
It doesn't natively handle more complex data types like specific datetime formats or categorical data like red, green, blue. Again, Pandas handles those. Its strict focus on homogeneous arrays means it's not suited for data structures where you need to mix different types like numbers and text within the same column or array.
Right, everything has to be the same type.
And crucially, NumPy is fundamentally an in-memory single-node library.
Meaning the data has to fit in your computer's RAM.
Yes, your entire NumPy array must fit entirely in the RAM of the single machine you're running it on. If you have datasets that are larger than your available memory, or if you need to distribute the computation across multiple machines in a cluster, NumPy alone won't cut it. You'd need to look at projects like Dask or Spark that can work with NumPy arrays in a distributed way.
Okay, so scalability is a limitation. What about parallelism? Can it use multiple CPU cores?
Some operations, particularly linear algebra routines that rely on optimized BLAS libraries, can leverage multi-threading automatically. But many of NumPy's core array operations are primarily single-threaded, so you don't always get automatic parallel speedups across all your CPU cores just by using NumPy.
And it's CPU only, right? No built-in GPU support.
Correct. For GPU acceleration, which is vital for deep learning and some large-scale simulations, you'd need to use other libraries like CuPy, which mimics the NumPy API but runs on NVIDIA GPUs, or frameworks like JAX, TensorFlow, or PyTorch.
And maybe a learning curve?
Yeah, there is a learning curve, especially for beginners, to truly grasp vectorized thinking, how to avoid loops, and to understand the nuances of broadcasting. It takes a bit of practice to think in terms of array operations.
But these aren't really flaws, are they? They're constraints based on its goal.
Exactly. There are natural constraints given NumPy's focused scope. It's intentionally a foundational layer. It relies on other libraries like Pandas or Dask to provide those higher-level abstractions or scalability features. It's that fundamental engineering trade-off again. Optimizing for raw numerical performance inherently restricts flexibility, and that's precisely why these other libraries are needed to fill the gaps.
It makes NumPy one of the most essential tools, though. You pretty much can't do data science in Python without encountering it.
Absolutely. Its impact on the Python ecosystem is immense. Python's rise as a leading data science language is largely credited to NumPy unlocking fast numeric computing, making it a viable alternative to proprietary tools like MATLAB.
It made the switch possible without losing speed.
Precisely. Practically every significant machine learning or scientific Python library uses NumPy directly or is heavily influenced by it. Even if a data scientist spends most of their time in Pandas manipulating data, as soon as they need to compute, say, a matrix correlation, or implement a custom mathematical function for a model, they're likely converting parts of their Pandas data frame into NumPy arrays to do the calculation efficiently.
And the community support must be huge.
Massive.
Okay.
Its ubiquity means countless tutorials, Stack Overflow answers, and examples. It's considered a foundational skill, often taught right at the start of data science courses, because understanding NumPy truly unlocks the potential of the rest of the ecosystem. It's that silent workhorse powering analytics everywhere.
Okay, so from NumPy, that silent high-performance engine for numbers, let's seamlessly transition to Pandas. I like to call this the go-to data manipulation and analysis powerhouse.
That's a perfect description.
If NumPy is the raw engine, Pandas feels more like the sophisticated dashboard and control panel for handling your data.
That's a really great analogy. Pandas' core purpose is providing these high-level, user-friendly data structures. Primarily, you've got the data frame for tabular, spreadsheet-like data, and the series for one-dimensional sequences or columns.
So bringing spreadsheets into Python.
You can absolutely think of it that way, bringing spreadsheet and database-like capabilities into Python, but with vastly more programmatic power and flexibility.
What's its core philosophy then? How does it differ from NumPy?
Its philosophy really emphasizes flexibility, powerful indexing and selection, intelligent data alignment, and very importantly, graceful handling of missing data. This is a key contrast to NumPy's raw array. Pandas introduces labeled axes, row labels, the index, and column labels, which NumPy fundamentally doesn't have.
Ah, the labels. That seems crucial for real-world data.
It is. Wes McKinney, its creator, articulated its goal perfectly. He wanted Pandas to be the fundamental high-level building block for doing practical, real-world data analysis in Python.
Practical, real-world. That sounds key.
It really captures its spirit. Pandas is designed to efficiently turn those often messy, incomplete, real-world data sets into structured, insight-ready forms. It empowers users to clean and shape data without, as Wes put it, going crazy, trying to manage everything in raw arrays or basic lists.
So it tackles the messiness head-on.
Exactly. The genius of Pandas wasn't just bringing data frames to Python, it was making the messy reality of data inherently manageable through things like intelligent label-based indexing and alignment. That revolutionized how we actually work with data day to day.
And the origin story is pretty cool, right? Didn't it start in finance?
It did. Wes McKinney started developing Pandas back in 2008. He was working at AQR Capital Management, which is a quantitative hedge fund.
Ah, a quant fund. They deal with tons of data.
Precisely. And at that time, Python really lacked a robust, high-performance tool specifically for financial data analysis. Wes needed something that could handle time series data really well, along with tabular data, all with labeled columns and rows, something like R's data frames or Excel, but integrated with Python and leveraging NumPy speed underneath.
So he just built it himself.
Pretty much. He built Pandas from the ground up to meet this demanding need for flexible, high-performance quantitative analysis on financial data. He open-sourced it in 2009, which is huge for the community.
Wow. And it took off from there?
It did. By 2015, it had become so central to data science that it joined NumPy as a fiscally sponsored project, getting that crucial organizational support.
And the name Pandas, is it about the animal?
No, fun fact, it actually derives from panel data. That's a term from econometrics for multidimensional time series data. It reflects its original strength in handling time-indexed financial data.
Panel data. Okay, that makes more sense. And it's still evolving.
Oh, yeah. As of 2025, we're in the 2.x release series. There's ongoing work, including exciting integration with technologies like Apache Arrow, which aims to make memory interchange between different systems even faster and more standardized.
So Arrow helps it talk to other data tools even better.
That's the goal, yeah. Improving interoperability and performance, like a classic story, really an industry-specific problem, drives this foundational open-source innovation.
The demands of finance pushed its design.
Definitely drove its initial robust design. High performance, handling time series, dealing with missing data gracefully. These were critical for finance. Then open sourcing it and getting that community support, especially through NumPy, allowed it to evolve into the general purpose powerhouse it is today. It's a fantastic example of successful open source development.
Was there any key internal change that made a big difference?
A critical internal architectural evolution was the introduction of something called the block manager back around 2011. We don't need to get into the super technical details, but conceptually it was a major innovation. It's how Pandas manages the underlying NumPy arrays efficiently, especially when you have columns with different data types in the same data frame, like numbers in one column, text in another, dates in a third.
Right, heterogeneous data. NumPy itself needs homogeneous arrays.
Exactly. The block manager cleverly groups columns of the same data type together into separate NumPy arrays blocks under the hood. This lets Pandas leverage NumPy's speed for each block, even though the overall data frame looks mixed to the user.
Ah, that's smart. Like organizing tools by type in a toolbox?
Kind of, yeah. It was a big step up in performance and memory management compared to earlier versions. And even today, The developers are always thinking about internal improvements, maybe even replacing the block manager eventually with something simpler and potentially faster.
Okay, so let's talk about the things users interact with directly. The main structures are the series and the data frame, right?
Correct. The series is your fundamental one-dimensional structure. Think of it as a single column from a spreadsheet, but with an extra piece, an index attached to each value.
An index, like row numbers.
It can be row numbers, 0, 1, 2, 2, but it can also be custom labels like dates, names, or IDs. That index is really powerful.
And the data frame.
That's the two-dimensional table, your classic spreadsheet structure. It has both row labels, the index, and column labels. You can think of a data frame as a collection of series objects, all sharing the same index.
Okay, series is one column, data frame is the whole table.
Yeah.
What's this label awareness thing you mentioned?
This is where Pandas gets really clever and saves you from a lot of potential errors. It's about automatic data alignment based on labels.
How does that work?
Say you have two series, maybe representing sales figures for different products, indexed by product ID. If you try to add these two series together, Pandas won't just add the first element to the first, second to the second, etc.
Right, what if the products are in a different order?
Exactly. Pandas looks at the index labels. It aligns the values based on matching product IDs before performing the addition. If one series has a product ID that the other doesn't, the result for that ID will be NaN, not a number indicating missing data.
Oh, wow. So it prevents you from accidentally adding apples and oranges just because they were in the same position.
Precisely. It makes combining and manipulating data much safer and more intuitive, especially when dealing with datasets that might not be perfectly ordered or complete. This label alignment is a cornerstone of Pandas.
That sounds incredibly useful. So internally, a data frame is like a dictionary of these series.
That's a good way to think about it conceptually, yes. A dictionary where the keys are the column names and the values are the series objects representing the columns, all sharing that common row index. And underneath, the block manager is organizing those series underlying NumPy data into efficient blocks based on data type.
Got it. Beyond the series and data frame, what other key components does Pandas offer?
Well, there are the powerful index objects themselves, which enable really flexible data selection. You have methods like .lock for selecting data based on labels, like row or column names.
Okay, .lock is for labels.
And .ilock for selecting data based on integer position, like the jrth row, first column. This distinction trips people up sometimes, but it's very powerful once you get it.
.ilock for position.
Then there's a whole suite of comprehensive I/O functions. Read ECSV, resexcel, resquicel, reJSON, you name it. Makes getting data into and out of Pandas data frames really easy.
Essential for starting any analysis.
Totally. Plus, robust data cleaning methods like dropna to remove missing values and fillmarnot to replace them. And an incredibly powerful Group B functionality.
Ah, Group B. I hear that mentioned a lot.
It's central to data analysis. It follows a split-apply-combine pattern. You split your data frame into groups based on the values in one or more columns. You apply some function, like calculate the mean, sum, count, or even a custom function, to each group independently, and then you combine the results back into a new data frame or series.
So you can easily calculate things like average sales per region or total counts per category.
Exactly. It's highly optimized, often using Cython under the hood for speed. Pandas also boasts an excellent time series module, inherited from its financial origins, with tools for resampling data to different frequencies, calculating rolling windows like moving averages, and handling time zones.
Which is why it's still huge in finance.
Absolutely. And finally, it even has convenience plotting methods like df.plot, which wrap Matplotlib functions to let you create quick visualizations directly from your data frames.
So it really tries to be a one-stop shop for data wrangling and initial exploration.
That's a good way to put it.
And its interoperability, it's built on NumPy, you said.
Fundamentally, yes. Pandas data structures use NumPy arrays internally to store the actual data. So it directly benefits from NumPy's raw computational performance for the numerical aspects.
And this integration is seamless. Data flows easily.
Very much so. You can take the values from a Pandas series or data frame column, which are essentially NumPy arrays, and feed them directly into Scikit-learn models without any explicit conversion usually needed.
Nice.
Pandas also integrates tightly with Matplotlib for its plotting methods, as we mentioned. And Seaborn, which we'll get to next, is often designed to work beautifully with tidy data frames prepared using Pandas.
So Pandas often acts as the central hub.
Yeah, I often think of it as the central data hub in the ecosystem. It's fantastic at ingesting data from all sorts of formats: CSVs, JSON, SQL databases, Excel files, web APIs.
Gets the data in.
Right. Then you use Pandas to clean, transform, and reshape it. And then you feed that prepared data downstream to other libraries, maybe Matplotlib or Seaborn for visualization, or Scikit-learn for modeling.
It connects the different stages.
Exactly. It acts as that bridge or glue library. It also has a smart dependency system. Core dependencies like NumPy are required, but many others for specific file formats or features are optional, so you only install what you need, keeping it adaptable.
Okay, so its sweet spot is structured data needing manipulation. What are the main use case domains where you'd reach for Pandas first?
Well, its absolute bread and butter is data cleaning and preparation. Reading raw data, handling missing values, NANs, fixing inconsistencies, changing data types, reshaping tables like pivoting or melting, filtering rows or columns, creating new features from existing ones, feature engineering. This is where Pandas shines and probably saves data scientists the most time.
The data janitor work, as they say.
Exactly, but a very powerful janitor. It's also paramount for exploratory data analysis, EDA. Doing quick summaries with df.describe, getting value counts with value counts, calculating correlations, slicing and dicing the data to understand distributions and relationships before you build any complex models.
Getting a feel for the data.
Precisely. Given its strong time series support, it's heavily used in time series and financial data analysis, resampling stock prices, calculating rolling averages or volatility, aligning trades.
Right, its origins.
And for small to medium scale ETL, extract, transform, load tasks, especially in scripts or notebooks, it can act as a lightweight in-memory database, reading data from one source, transforming it, and writing it out somewhere else.
Useful for automation.
Yeah. And of course, it's crucial for preparing the input to machine learning models, getting your data into that nice rectangular format of a feature matrix, X, and a target vector, Y, that libraries like Scikit-learn expect.
So preparing the final data set for the model, it sounds incredibly versatile. What are its biggest strengths?
I'd say expressiveness and convenience are huge. You can often accomplish complex data manipulations with just 1 or 2 lines of Pandas code, which makes data scientists incredibly productive.
Less code, faster iteration.
Exactly. It provides rich functionality. It's practically that one-stop shop for most data wrangling needs, from I/O to merging, filtering, grouping, and time series analysis. It handles heterogeneous data gracefully, unlike NumPy's arrays. Its label indexing and automatic alignment are powerful features that prevent many common errors and save debugging time.
That alignment feature seems like a lifesaver.
It really is. Pandas also has very robust missing data handling, which is crucial because real-world data is almost never perfect. And for the tasks it performs, it's generally optimized for performance, leveraging Python and C under the hood for critical operations. It can handle data sets up to, say, a few million rows quite efficiently, provided they fit in memory.
And in the community?
Excellent documentation and a massive active community. If you have a Pandas question, chances are someone has already asked and answered it online.
Okay, but it can't be perfect. What are the limitations or trade-offs with Pandas?
Right, no tool is perfect. A major one is memory usage. Because it offers flexibility with mixed types and labels, it has more overhead than raw NumPy arrays. For very large data sets, this overhead can become significant and you might run out of RAM.
So it can be memory hungry.
It can be, especially compared to NumPy or more specialized databases. And related to that, like NumPy, it's fundamentally a single machine in-memory library. It doesn't automatically scale out to clusters for truly big data, think terabytes or petabytes. For that, you need tools like Dask, which provides a Pandas-like API for distributed computing, or Apache Spark.
Okay, so not for massive scale on its own.
Correct. Also, while generally fast, it can become slow for non-vectorized operations. If you find yourself writing loops to iterate row by row over a data frame, you're likely losing most of the performance benefits. You really want to stick to its built-in vectorized functions.
Avoid Python loops in Pandas. Got it.
The API itself can have complexities, especially around indexing the difference between .lock, .ilock, and when indexing returns a view versus a copy, can sometimes trip up even experienced users.
Yeah, I've heard about the view versus copy warnings.
Exactly. And it's generally not multi-threaded by default for most operations, so it doesn't automatically exploit all your CPU cores for parallelism like some other systems might. Finally, it's not designed for real-time updates or streaming data. Operations typically create new copies of data rather than modifying it in place efficiently.
So again, trade-offs for flexibility and ease of use.
Precisely. It inherently trades some raw performance and scalability for incredible flexibility and productivity for the vast majority of common, moderate-sized data analysis tasks, and that trade-off is usually well worth it.
Its real-world relevance seems undeniable then. It basically enabled Python for serious data analysis work.
Many would say it was a game changer. Yeah. It brought Python to parity with languages like R for data manipulation and analysis. It dramatically speeds up that data cleaning and preparation phase, which often consumes the bulk of a data scientist's time.
Freeing them up for the actual analysis.
Exactly. It's ubiquitous in industry finance, tech analytics, bioinformatics, social sciences, and you see it constantly in production pipelines for moderate data sizes. Pandas proficiency is almost always listed as a required skill in data science job postings.
It's table stakes now.
Pretty much. It also spurred innovation, inspiring libraries like Dask and Vakes to tackle its scaling limitations. And its data frame API has influenced how other systems, like Spark, design their Python interfaces. Its role as the data janitor is just critical because garbage in, garbage out, right? The quality of your analysis and models depends entirely on the quality of the data you feed them, and Pandas is the primary tool for ensuring that quality.
Okay, we've got our data clean and structured with NumPy and Pandas. Now we need to see it, to understand it visually. Let's shift focus to Matplotlib, which you described earlier as the fundamental plotting library in Python.
That's right. It really is the artistic foundation upon which so much other visualization is built in the Python world.
So what's its core purpose? What problem was it trying to solve?
Its main purpose is straightforward, creating a huge variety of data visualizations, static plots, animated plots, even some basic interactive plots.
Like charts and graphs.
Exactly. Line charts, bar charts, scatter plots, histograms, heat maps, you name it. It was originally inspired, quite heavily actually, by MATLAB's plotting capabilities. The name Matplotlib is a bit of a giveaway there.
Ah, MATLAB plotting library. Makes sense.
But its design philosophy is interesting because it's kind of dual-pronged. This is really important to grasp.
Okay, two sides to it.
Yeah. First, there's the ease of use aspect. This is mainly achieved through the PyPlot module, typically imported as PILT. This provides a high-level, state-based interface that closely mimics MATLAB's plotting commands.
State-based. What does that mean?
It means Matplotlib keeps track of the current figure and axis you're working on implicitly. So you can just call plt.plot or plt.title, and it applies to the current plot without you needing to manage plot objects explicitly. This makes simple, quick plots incredibly straightforward. The goal was easy things easy.
Okay, PyPlot for quick and easy. What's the other side?
The other side is flexibility and power. This comes from its comprehensive object-oriented API. This gives you granular, almost pixel-level control over every single element in your plot.
Every line, every label.
Every line, label, tick mark, title, legend entry, everything. Matplotlib calls these visual elements artists. There are primitive artists like lines and text, and container artists like the figure, which is your entire canvas, maybe containing multiple plots, and the axis, which represents a single plotting area with its own coordinate system.
Figure is the canvas. Axes are the individual plots on it.
Exactly. This object-oriented approach is what makes hard things possible. It allows you to create incredibly complex, customized publication-quality graphics. It also enables platform-agnostic output. You can save plots as PNGs, JPEGs, PDFs, SVGs, and integration with graphical user interface, GUI toolkits like Qt or Tkinter via different backends.
So ultimate control if you need it.
That's the idea. The overarching design aims for consistency and completeness, allowing you to plot, theoretically, any array of numbers in any way you want.
And the history behind Matplotlib is also quite interesting, isn't it? Driven by a scientist's frustration.
It is. Very relatable. It was created by John D. Hunter back in 2003. He was a neurobiologist, and he needed to analyze complex EEG and ECOG brain data from his research.
Okay, brain signals.
Right. And he was incredibly frustrated because his lab had only a single license for an expensive proprietary analysis software, and it required a physical hardware dongle. It was a huge bottleneck for their work.
Oh man, the dongle days, I remember those.
Exactly. He tried using MATLAB, but found its array-centric view wasn't ideal for the complex, sometimes heterogeneous medical data he was dealing with. He needed something more flexible.
So dissatisfaction led him to Python.
It did. He started developing a plotting library within Python, initially just as a component for a new scientific application he was building for his own research needs. He wasn't setting out to create a general plotting library at first.
But he realized it could be more broadly useful.
Exactly. He quickly recognized his potential as a general-purpose plotting tool for the wider scientific Python community, many of whom were also looking for free, powerful, open-source alternatives to MATLAB or other commercial packages. So he open-sourced Matplotlib in 2003.
And it caught on.
It gained traction very rapidly. It became a vital part of that growing SciPy ecosystem. Key milestones were the release of Matplotlib 1.0 around 2007 and a highly influential paper published in the Journal of Machine Learning Research, JMLR, that year, which really announced it to the academic world and significantly boosted its visibility.
So it became the standard quite quickly.
Pretty much. Sadly, John Hunter passed away prematurely in 2012. But before that, he had nominated Michael Droitboom as the lead developer, and a larger core team took over stewardship, ensuring its continued active development.
So the project lived on.
Absolutely. It's now well into its 3.x release series, still actively developed and fiscally sponsored by NumPy. And here's something truly surprising that speaks volumes about its importance. In 2024, NASA actually awarded a grant specifically to support Matplotlib's development.
NASA funded Matplotlib? Why?
They recognize it as critical open-source infrastructure for science. That's a huge validation. While it inspired higher-level libraries like Seaborn, Matplotlib remains absolutely foundational. It's the canvas for virtually all static plotting in Python.
That's incredible. Okay, let's dig into the architecture a bit more. You mentioned this three-layered stack.
Right. Understanding these layers helps clarify how Matplotlib achieves its flexibility. At the very bottom, you have the backend layer.
The backend, what does that do?
This is the lowest level. It's responsible for the actual rendering, translating the abstract plot description into pixels on your screen or vector graphics in a file. It interfaces with the operating system's drawing toolkits or specific file formats. It handles the how to draw part. Matplotlib uses different backend renderers. A common one for generating static files is egg, which uses the C++ anti-grain geometry library for high-quality anti-alias pixel output consistently across different platforms.
So the backend handles the actual drawing. What's next?
Above that is the artist layer. This is the heart of Matplotlib. It's object-oriented core. Everything you see on a Matplotlib plot is an artist object.
Everything, like the lines, the text?
Lines, text, tick marks, axes, titles, legends, the figure itself. They're all artist objects, organized hierarchically. The figure artist is the top-level container, the overall canvas. An axis artist is a sub-region within the figure where you actually plot your data. You can have multiple axes on one figure, like subplots. This hierarchical structure of artists is what gives you that fine-grained control. This layer essentially defines what to draw.
Okay, backend is how to draw. Artist is what to draw. What's the top layer?
The top layer is the scripting layer, which is the familiar PyPlot API, import matplotlib.pyplot as PLT. This is the user-friendly, state-based interface we talked about earlier.
The one that mimics MATLAB.
Exactly. Functions in PyPlot implicitly keep track of and modify the current figure and axis. If you call plt.plot, it draws on the current axis. If you call plt.title, it sets the title of the current axis. It abstracts away the explicit creation and management of figure and axis objects for simplicity.
Makes simple plots easy.
Yes, but for very complex plots with multiple figures or subplots, relying solely on the stateful PyPlot API can sometimes lead to confusion about which plot element is being modified.
Yeah.
That's why for complex visualizations, the object-oriented approach, explicitly creating and working with figure and axis objects, is often recommended.
Because you have both options.
Precisely. This layer design is critical. It ensures Matplotlib is both versatile, capable of simple scripts and complex applications, and portable, able to render to many different outputs.
And fundamentally, it expects data as NumPy arrays, right?
Yes, it's built directly on NumPy. It expects the data you want to plot to be passed in as NumPy arrays or objects that can easily be converted into them, like Python lists. This really solidifies how tightly interconnected these foundational libraries are.
And how does it play with Pandas and Seaborn?
The interoperability is crucial. As we mentioned, Pandas uses Matplotlib as its default plotting backend when you call df.plot on a Pandas data frame.
Pandas calls Matplotlib.
Yep, Pandas is internally constructing and calling Matplotlib functions to create that visualization. Similarly, Seaborn is built entirely on top of Matplotlib.
Seaborn uses Matplotlib as its engine.
Completely. Every chart you create with Seaborn is fundamentally a Matplotlib figure containing Matplotlib axes populated with Matplotlib artists. This is incredibly powerful because it means you are never locked into Seaborn's defaults or capabilities.
You can always tweak a Seaborn plot using Matplotlib commands.
Always. If Seaborn gives you 90% of what you want, you can grab the underlying Matplotlib axis object that Seaborn returns and use standard Matplotlib functions. Ax.setTotal, Ax.setLabel, Ax.grid, etc. to customize that remaining 10%.
That's really flexible.
It is. Matplotlib also integrates seamlessly with environments like Jupyter Notebooks using magic commands like %matplotlib inline, for static plots embedded in a notebook, or %matplotlib widget for basic interactive plots. It serves as the base plotting engine for countless other scientific Python projects, and its influence can be seen in plotting libraries in other languages too. Its ability to output standard image formats like PNG, PDF, great for vector graphics and papers, and SVG makes it easy to incorporate plots into automated reports or publications. Plus, the vast community knowledge and examples make it very robust.
So use cases are pretty broad then. Where do people typically use Matplotlib?
Virtually anywhere data visualization is needed, especially for static plots. It's incredibly popular for exploratory data analysis, EDA, creating quick histograms, scatter plots, line charts to get an initial understanding of data distributions, relationships, or trends over time.
The first look at the data.
Exactly. It's also the go-to tool for creating presentation and publication graphics. Because of its fine-grained control, you can customize plots to meet the exact, often stringent requirements of academic journals or professional reports.
Making plots look just right.
Precisely. In dashboards and monitoring, Matplotlib is often used in automated scripts to generate static images like performance charts or model diagnostic plots that might be embedded in daily reports or web dashboards. And it's widely used for educational purposes, both for teaching data visualization itself and for illustrating concepts in math, physics, engineering, and other fields.
It's versatile, and you mentioned its role in big science projects too.
Yes. That Event Horizon Telescope project using Matplotlib for visualizing data related to the first image of a black hole is a powerful example. It shows a level of trust the scientific community places in Matplotlib for critical, high-stakes endeavors. It's also used in more specialized domains like geospatial plotting through libraries like Cartopy, which builds on Matplotlib, and for creating basic 3D wireframe or surface plots. It's really the underlying workhorse.
Okay, let's talk strength. Completeness and flexibility seem key.
Absolutely. Its biggest strength is its sheer completeness and flexibility. You can, with enough effort, create almost any static 2D visualization you can imagine. It offers incredibly fine-level control over every aspect: lines, colors, fonts, ticks, labels, layout, everything.
Allowing for true publication quality output.
Exactly. It's cross-platform and supports a wide range of output formats, raster and vector, and GUI integrations. Matplotlib is also known for its stability and maintenance. It has a robust testing framework and a strong commitment to backward compatibility, which is crucial for reproducibility in science and long-term projects.
Your old code is likely to keep working.
Generally, yes. And the huge community and documentation is a massive asset. Countless examples, tutorials, and Stack Overflow answers are readily available. Even if you primarily use higher-level libraries, Matplotlib often remains the common denominator, a reliable fallback. And many other libraries return Matplotlib objects, allowing you to use your Matplotlib knowledge to tweak their output.
But that flexibility must come with trade-offs, right? What are the limitations?
It does, and it's an interesting trade-off. The very flexibility can make its API, especially the object-oriented side, feel quite verbose and less user-friendly compared to more declarative libraries. Sometimes it feels like you're writing a lot of code just to get a basic plot customized the way you want.
More boilerplate code sometimes.
Can be, yes. Its MATLAB-inspired stateful interface, PyPlot, while simple for quick plots, can sometimes cause confusion in more complex scenarios, like managing multiple subplots, if you're not careful about which figure or axis is currently active.
Easy to accidentally modify the wrong plot.
It can happen if you're not using the object-oriented style consistently. Historically, its default aesthetics were quite basic and, frankly, not very visually appealing out of the box.
They looked a bit dated.
Yeah, you often had to do a lot of manual tweaking to make plots look professional. They've significantly improved the defaults in recent versions, like with version 2.0. But many users still prefer the defaults offered by libraries like Seaborn or apply custom style sheets.
Okay, what else?
Matplotlib is primarily a 2D plotting library. While it has some basic 3D capabilities like scatter, surface, wireframe plots, they're less developed and perhaps less intuitive than dedicated 3D visualization tools. And while PyPlot offers basic interactive features like zooming and panning in certain backends, Matplotlib is fundamentally geared towards creating static images, not complex, interactive, web-based charts like libraries such as Plotly or Bokeh specialize in.
So not for dynamic web dashboards.
Not its primary strength. For extremely large data sets, plotting can sometimes be slow because Matplotlib, by default, tries to draw every single data point. It doesn't have sophisticated built-in downsampling or aggregation techniques for handling millions or billions of points efficiently. Finally, Because it's so general and gives you so much control, it doesn't inherently guide you towards good visualization practices. It's easy to make cluttered or misleading plots if you don't know the principles of effective data visualization.
So it gives you the power, but also the responsibility to use it wisely.
Exactly. Matplotlib sacrifices some out-of-the-box simplicity and modern interactivity for unparalleled power, control, and generality. It makes it incredibly potent once you invest the time to master it.
Its real-world relevance sounds immense, though. Standard tool for decades.
Absolutely. It's been the default plotting tool for Python users for over 20 years. Virtually every Python data scientist knows at least the basics. That NASA grant we mentioned really underscores its status as critical infrastructure.
Used everywhere in science and engineering.
Countless publications, research projects, engineering analyses rely on it. The Event Horizon Telescope example is just one high-profile case. And in industry, it's widely used for visual diagnostics, internal reporting, and quick visualizations during development.
And you mentioned it enabled other libraries.
Yes, that's a crucial aspect of its real-world relevance. Matplotlib handled the difficult problem of rendering plots consistently across platforms. This allowed other libraries like Pandas and Seaborn to focus on their specific domains, high-level data manipulation or statistical plotting, and simply use Matplotlib as their rendering engine.
They didn't have to reinvent the plotting wheel.
Exactly. This layered approach accelerated innovation in the entire Python data science ecosystem. It cemented Matplotlib's role as the workhorse of plotting. Maybe not always the flashiest, but incredibly dependable and comprehensive. Knowing Matplotlib gives you the power to understand and potentially tweak almost any plotting code you encounter in the Python world.
Okay, so if Matplotlib is the fundamental canvas and brush set, giving us ultimate control but maybe requiring more effort, let's talk about Seaborn. You described this as the library that makes statistical graphics attractive and informative.
That's a great way to think about it.
It sounds like it builds on Matplotlib, but focuses specifically on statistical plots. Maybe makes them easier or prettier.
Precisely. Seaborn is a high-level data visualization library built directly on top of Matplotlib. Its core purpose is to simplify the creation of aesthetically pleasing and crucially informative statistical graphics.
So it's designed to fix some of Matplotlib's pain points.
Exactly. Particularly for visualizing complex data sets or relationships where you need to incorporate statistical understanding, things like distributions, relationships between multiple variables, comparisons between groups, uncertainty.
What's its philosophy then? How does it achieve this simplicity?
Its core philosophy really centers on two things. Simplicity for the user aiming to achieve complex visualizations with just one or two function calls, and sensible default aesthetics.
Meaning it looks good out of the box.
Yes, the goal is that your plots are visually appealing and often publication quality with minimal extra tweaking. It has strong opinions about good visual design for statistical plots. It also features a dataset-oriented API.
Dataset-oriented. What does that mean compared to Matplotlib?
It means Seaborn functions are designed to work directly with entire datasets, most commonly Pandas data frames. You typically pass the whole data frame to the function and then specify which columns should be mapped to which visual properties like x-axis, y-axis, color, size, style, using column names as strings.
So you say X my column name, your other column, hue category column.
Exactly. Seaborn then handle all the internal grouping, mapping, and often performs statistical estimations automatically based on those column specifications. This leads to a more declarative style of plotting.
Declarative, as in you say what you want, not how to draw it step by step.
Precisely. You declare, for example, I want to plot the relationship between variable x and variable y, colored by the categories in variable z, and please show me the regression line and its confidence interval. Seaborn figures out how to fetch the data, group it, calculate the statistics, and then uses Matplotlib under the hood to draw the plot.
Can you give an example?
Sure. A function like sns.regplot, data mydf, x col a, y col b, can create a scatter plot of col a versus col b, automatically calculate and draw the best fit linear regression line, and shade the 95% confidence interval around that line all in one go.
Wow. Doing that in pure Matplotlib would be way more code, right? You'd have to calculate the regression yourself.
Oh yeah. You'd need to probably use NumPy or SciPy to fit the line, calculate the interval bounds, then plot the points using plt.scatter, plot the line using plt.plot, and maybe fill the confidence band using plt.fillbetween. Seaborn abstracts all that complexity away for common statistical tasks.
That's a huge productivity boost. And who created Seaborn? Was it also a scientist?
It was. Created by Michael L. Wascom, also a neuroscientist, around 2013-2014. And much like John Hunter with Matplotlib, Wascom was motivated by finding Matplotlib somewhat verbose for the specific kinds of statistical plots he needed for his own research data.
So necessity is the mother of invention again.
Seems to be a theme. He effectively filled a niche in the Python ecosystem. At the time, R had the very popular ggplot2 library, known for its power in creating sophisticated statistical graphics with a declarative grammar. Seaborn provided a Pythonic equivalent, making Python much more attractive for statisticians and data scientists coming from R or just wanting easier statistical plotting.
So it helped bridge the gap with R's plotting capabilities.
Significantly, it quickly became popular for its ease of use and those beautiful default styles. Wascom continues to be the lead maintainer. It's evolved over time, adding more plot types like violin plots, swarm plots, pair plot for matrix scatter plots, better theme customization, and tighter Pandas integration.
Any recent big changes?
A significant recent development, starting around Seaborn version 0.12 in 2022, was the introduction of an experimental new object-oriented interface, sometimes called the objects interface, plot, layer. This aims to provide a more composable and potentially even more flexible way to build plots, perhaps moving a bit closer philosophically to ggplot2's grammar of graphics, while still leveraging Matplotlib underneath. It shows the library is still actively refining its approach.
Interesting. So this tight coupling with Matplotlib using it underneath, that has pros and cons.
Definitely. The big pro is that Seaborn benefits directly from all the power and improvements in Matplotlib, better text rendering, new color maps, backend support, etc., without having to reinvent any of that low-level rendering code. It also means users can always use their Matplotlib knowledge to customize Seaborn plots.
Right. You can always drop down a level. What are the cons?
The main con is that Seaborn inherently inherits Matplotlib's limitations. Since it uses Matplotlib for drawing, it's primarily geared towards static 2D plots. It doesn't magically gain interactive web capabilities or advanced 3D plotting just because it's Seaborn. Its performance on very large datasets can also be limited by Matplotlib's underlying rendering performance.
So it's bound by what Matplotlib can do?
Essentially, yes.
Yeah.
But within that scope, Seaborn provides a massive improvement in convenience and aesthetics for statistical visualization. It really filled that crucial gap between raw Matplotlib and the practical needs of data analysts and scientists, quickly becoming a staple tool. It set a new standard for what high-level plotting in Python could look like.
How is Seaborn's structure internally? You mentioned axes-level and figure-level functions.
Right. Architecturally, remember, it's a wrapper extension of Matplotlib, not its own renderer. It primarily offers two main types of plotting functions.
Okay. First type.
Axis-level functions. These are functions like sns.scatterplot, sns.histplot, sns.boxplot, sns.bartplot. Each of these functions draws a specific type of plot onto a single Matplotlib axis object.
So they operate on one plot area.
Exactly. They typically take your data, often a data frame and column names, perform any necessary internal calculations, like bidding for a histogram or calculating median score tiles for a box plot, and then they call the relevant low-level Matplotlib routines to draw the shapes, lines, points, etc. onto the axis. Crucially, these functions return the Matplotlib axis object they plotted on.
Why is returning the axis object important?
Because it allows you, the user, to immediately apply further customizations using standard Matplotlib methods directly on that returned axis object, like ax.setTitle, myTitle, or ax.setSlim0100.
Enables that seamless drop-down to Matplotlib customization. Got it. What's the second type of function?
Figure-level functions. These are higher-level functions like sns.relplot for relational plots like scatter or line, sns.displot for distributions, sns.catplot for categorical plots, sns.jointplot shows relationship and individual distributions, and sns.pairplot, matrix of pairwise relationships.
These sound more complex. How are they different?
These functions create an entire Matplotlib figure, which might contain multiple axes, subplots, arranged in a grid. They're particularly useful for creating faceted plots, where you automatically create subplots based on the levels of some categorical variable. They manage the overall figure layout, shared axes, legends, and titles across the subplots.
So they orchestrate multiple plots together. What do they return?
They typically return a Seaborn object, like a facet grid or pair grid or a joint grid. These objects contain the underlying Matplotlib figure and axes, which you can still access if you need deep customization, but the primary interaction is often through methods on the Seaborn grid object itself, like grid.setTitles.
So two levels, single plot, axis level, returning an axis, or multi-plot grid, figure level, returning a Seaborn grid object.
Exactly. Underlying both are often internal statistical computation modules. Many Seaborn plots aren't just drawing raw data. They're computing things first. SNS.regplot fits a regression. SNS.kdplot computes a kernel density estimate. SNS.barplot computes means and confidence intervals. Seaborn uses libraries like NumPy, SciPy, and sometimes stats models to perform these calculations transparently before plotting.
So the statistics are built in for many plots.
Yes. And finally, a big part of Seaborn is its sophisticated themes and color management. It provides predefined themes, SNS.setTheme, and a wide variety of carefully designed color palettes that automatically adjust Matplotlib's default parameters, or CPRMs, to achieve those visually appealing publication-ready aesthetics. This centralizes control over the look and feel.
Makes styling easy and consistent.
That's the goal.
Yeah.
Overall, it's a clever layer above Matplotlib that intelligently manages data mapping, statistical transformation, and aesthetic defaults, orchestrating Matplotlib's drawing capabilities without replacing its core.
Okay, and interoperability. Built on Matplotlib, works great with Pandas.
Explicitly, it's designed to be tightly integrated. It primarily accepts Pandas data frames and lets you refer to columns by name, strings, which is incredibly convenient. Data make df, dash column A, y column B, hue category C.
That seamless connection is key.
Absolutely, and that point about every Seaborn plot being a Matplotlib object underneath is crucial. You can always drop down to Matplotlib for tweaks. If you call ax to sns.scatterplot, you can then use ax.setXlabel or plt.title if using the stateful API.
Ax are never stuck.
Right. Seaborn also influences Matplotlib's look. If you set a Seaborn theme, even your pure Matplotlib plots created afterwards will adopt that style. It plays beautifully in typical data science pipelines. Use Pandas for cleaning, maybe Scikit-learn for modeling, then Seaborn to visualize the results, plotting confusion matrices, feature importances, model performance curves, residual plots, etc.
Visualizing the ML outputs.
Very common use case. And its core dependencies are quite light, mainly Matplotlib, NumPy, SciPy, and Pandas.
So where is Seaborn most heavily used? What are its prime domains?
Perhaps its number one use case is exploratory data analysis, EDA. It excels at quickly visualizing distributions, histograms, KDEs, box plots, relationships between variables, scatter plots, regression lines, and comparisons across different groups or categories within your data.
Faster insights during exploration.
Definitely. It's also vital for statistical analysis and reporting, illustrating findings from statistical tests or models, often showing confidence intervals or regression results directly on the plot, making it great for academic papers or business reports where conveying uncertainty is important.
Communicating statistical results visually.
Yes. It's particularly strong for multivariate and complex plots. Functions like pairplot give you a quick overview of all pairwise relationships in your dataset, and using parameters like hue, size, and style allows you to encode multiple dimensions, often 3, 4, even 5 variables, into a single interpretable 2D plot.
Packing more information into one graphic.
Right. And as we mentioned, it's frequently used for machine learning workflow visualization, plotting things like confusion matrices using sns.heatmap, feature importances using sn.barplot, learning curves, or distributions of model predictions. And naturally, for presentation graphics for data storytelling, its polished, professional look is a significant advantage. It helps create compelling visuals without needing deep design expertise.
Makes your reports look better, faster.
Pretty much. It excels when you need high-level statistical visualization from structured data, aiming for plots that are both insightful and visually appealing right away.
Okay, summarizing the strengths. Productivity seems huge.
Massive productivity boost. Reduces the lines of code needed for common statistical plots dramatically. Excellent default aesthetics plots generally look good, often publication quality with minimal effort. The dataset-oriented API working with Pandas data frames and column names is very intuitive.
Built-in statistics.
Yes, the statistical estimation capabilities, means, CIs, regressions, integrated into many plotting functions are a major plus. It offers a comprehensive range of statistical plot types specifically designed for common analysis tasks. Seamless integration with Pandas and Matplotlib is key, and while the defaults are great, it still offers flexible customization through its own parameters and by allowing access to the underlying Matplotlib objects.
Sounds great. What about the limitations? Still bound by Matplotlib?
Yes, the primary limitation is its reliance on Matplotlib. It inherits Matplotlib's complexities for deep customization beyond what Seaborn's high-level API provides easily. If you need something very bespoke, you might still need to dive deep into Matplotlib artist manipulation.
Okay. What else?
While the built-in regression functions are great for visualization, they're primarily for visualizing trends. Not for rigorous formal statistical inference, you typically use libraries like stats models for that. It's not standalone. It requires Matplotlib. Performance for very large data sets can be slow or lead to cluttered plots, as it often tries to plot many points and might perform complex computations like KDEs. It's not for interactive visualizations beyond Matplotlib's basic capabilities. No native 3D or map plotting. And users still benefit greatly from needing Matplotlib understanding for deep customization. You can hit a wall if you only know Seaborn. Finally, it often works best when your data is in a tidy format, which might require some upfront data reshaping using Pandas if your data isn't already structured that way.
So tidy data is preferred. Again, it's a trade-off.
Exactly. Seaborn trades some of the raw, limitless flexibility of Matplotlib for a huge boost in productivity and visual appeal, specifically for statistical plotting. It fills a specific, crucial niche extremely well.
And in the real world, knowing Seaborn is pretty valuable.
Highly valuable skill, yes. It's ubiquitous in data exploration notebooks, Kaggle competition analyses, internal business reports, scientific publications, anywhere statistical insights need to be communicated visually and effectively. It significantly enhances your ability to tell stories with data.
It raised the bar for Python plotting.
It really did. It demonstrated how a high-level, statistically aware API could provide ease of use combined with depth, influencing other libraries. It was also crucial in making Python a more welcoming environment for users coming from R who are accustomed to ggplot2. It's often one of the very first libraries imported right after NumPy and Pandas import Seaborn as defense and Pandas, making sophisticated data visualization a routine, accessible part of the Python data science workflow.
All right, we've loaded our data with NumPy, cleaned and manipulated it with Pandas, explored it visually with Matplotlib and Seaborn. Now it's time for the learning part. Let's bring in our final foundational library, Scikit-learn, the comprehensive library for machine learning.
The workhorse of practical ML in Python, for sure. Scikit-learn, often imported as sklearn, provides simple and efficient tools for common machine learning tasks, and it does so with remarkable ease and consistency.
So it's not just one algorithm, it's a whole toolkit.
Exactly. Its core purpose is to streamline AI and machine learning workflows by offering a unified, consistent API for a broad range of supervised learning, like classification and regression, and unsupervised learning, like clustering and dimensionality reduction algorithms. Plus, it includes crucial utilities for things like data preprocessing, model selection like cross-validation, and model evaluation.
What was the situation like before Scikit-learn?
It was much more fragmented. ML implementations in Python were scattered across different research labs or individual projects, often with inconsistent interfaces, varying levels of documentation, and requiring deep expertise to even use, let alone implement reliably from scratch.
So Scikit-learn brought order to the chaos. What's its philosophy?
Its philosophy is built around simplicity, efficiency, and accessibility. It's designed to be easy enough for non-experts or beginners to pick up quickly, yet powerful and robust enough for serious research and even production use cases.
And that famous consistent API is key.
Absolutely central. The API is legendary for its consistency. Pretty much any model or estimator object follows the same pattern. You initialize the model object, using model logistic regression. You train it on your data using the .fitxy method, and then you make predictions on new data using .predictNew.
And .predict. Learn it once, use it everywhere.
Pretty much. Once you understand that basic workflow for one model, you can easily swap in dozens of others. Decision trees, support vector machines, random forests, gradient boosting, often just by changing the class name you import and initialize. It makes experimentation incredibly fast.
Does it have all the ML algorithms? What about deep learning?
That's a crucial point. Scikit-learn deliberately focuses on well-established, robust algorithms. Think of it as the greatest hits of classical machine learning. It intentionally does not include deep learning networks, like convolutional neural nets or transformers.
Why not?
That was a strategic choice. Deep learning requires different computational patterns, often heavy GPU usage, and has its own rapidly evolving ecosystem of specialized libraries like TensorFlow, PyTorch, and Keras. Scikit-learn decided to excel at classical ML rather than trying to do everything.
Focus on its strengths, and it's built to work with the others.
Yes, it's designed from the ground up to interoperate seamlessly with the scientific Python stack, especially NumPy arrays and SciPy sparse matrices, which it uses for data representation. Its name, Scikit, actually signifies a SciPy toolkit or extension package.
Ah, Scikit SciPy toolkit.
Exactly. Its mantra, stated in its documentation, sums it up. simple and efficient tools for predictive data analysis, accessible to everybody, and reusable in various contexts, built firmly on NumPy, SciPy, and Matplotlib.
And its origins, also a community effort.
It started quite humbly, actually, as a Google Summer of Code project back in 2007, initiated by David Cornipo. The initial goal was really about user-friendliness and integration.
Google Summer of Code. Wow, how did it grow from there?
It gained significant momentum when researchers at INRIA, the French National Institute for Research in Digital Science and Technology, got heavily involved around 2010. They really pushed its development forward, leading to the first public release, version 0.1 beta, in early 2010.
And then that JMLR paper.
Yes. A major milestone was the publication of a paper about Scikit-learn in the Journal of Machine Learning Research, JMLR, in 2011. This formally announced it to the academic and research world, established its credibility, and its popularity just exploded due to its clean design, comprehensive features, and excellent documentation.
It stayed in version 0.x for a long time, though, didn't it?
It did, remarkably long. It only reached version 1.0 in late 2021. That decade-plus of 0.x versions signaled a very strong commitment to backward compatibility and API stability, which is hugely valuable for people building long-term projects or production systems relying on it. You didn't have to constantly rewrite your code with every minor update.
That stability is a big plus, and you mentioned it deliberately didn't chase deep learning.
Right. That was a really notable strategic decision during its evolution, especially in the mid-2010s when deep learning was exploding. Instead of trying to bolt on GPU support or complex neural network layers, the Scikit-learn developers focused on strengthening its core, improving existing classical algorithms, adding better cross-validation tools, refining the pipeline functionality for robust workflows, improving support for different data types.
Doubling down on classical ML and the workflow around it.
Exactly. This solidified its reputation as the undisputed go-to library for classical machine learning tasks. It was a smart move, acknowledging that not every problem needs a massive neural network, and providing high-quality, reliable tools for the vast range of problems where classical methods excel or provide strong baselines. It has a very strong community, is also fiscally sponsored by NumPy, and is taught extensively in universities worldwide.
So architecturally, what makes it tick? Beyond .fit and .predict.
Okay, under the hood, it relies heavily on NumPy for dense arrays and SciPy for sparse matrices to represent data efficiently. Many of the computationally intensive algorithms are actually implemented in Python.
Python, what's that?
Python is a language that makes it easy to write C extensions for Python. So, Scikit-learn uses Python to write performance-critical code that compiles down to fast C, often wrapping battle-tested CC++ libraries like libsvm and liblinear for support vector machines, or using optimized C code for decision trees. This gives Python users the speed of C without having to write C themselves.
Ah, another example of using compiled code for speed.
Yes, it's crucial for ML performance. But the real architectural genius, I think, is the estimator API.
The estimator API, tell me more.
An estimator is basically any object in Scikit-learn that can learn from data. This includes the actual learning algorithms, classifiers, regressors, clusterers, but also things like preprocessing tools, scalars, encoders, imputers, and even dimensionality reduction techniques. They all inherit from a base estimator class and expose that consistent .fit method to learn parameters from data.
So pre-processing steps are estimators too?
Many are, yes. Specifically those that learn parameters from the data, like a standard scalar learning the mean and standard deviation, or PCA learning the principal components, implement .fit. Then estimators are further categorized. You have classifier mixin and regressor mixin, which provide the .predict method, and often you have proba for classifiers, and a score method for default evaluation. You also have the transformer interface, used heavily by pre-processing steps, which provides a .transform method to apply the learning transformation to new data, and often a convenient .fit transform method.
Okay, so this consistent structure, estimator, classifier, regressor, transformer makes everything standardized.
Exactly. It standardizes all the components, making them swappable and composable. You can easily try different pre-processing steps or different models within the same workflow structure. Algorithms are organized logically into submodules like Scikit-learn.linear model, Scikit-learn.ensemble, Scikit-learn.cluster, etc.
And the workflow aspect, you mentioned pipelines.
Yes. The pipeline object is incredibly powerful and really promotes good ML practice. It allows you to chain multiple steps, typically one or more transformers, for pre-processing feature selection, followed by a final estimator model into a single compound estimator object.
What's the benefit of chaining them in a pipeline?
Several huge benefits. First, Convenience.break Scikit once on the entire pipeline. Second, preventing data leakage. It ensures that steps like fitting scalars or feature selectors only happen on the training data within each fold of cross-validation, preventing information from the test set leaking into the training process, which is a common and subtle bug. Third, reproducibility. It encapsulates your entire pre-processing and modeling workflow in one object, making it easier to save, load, and reuse consistently.
Wow. Pipelines sound essential for robust work.
They really are. Scikit-learn also provides comprehensive tools for model selection and evaluation, things like train-a-split for basic holdout validation, various cross-validation strategies, K-fold, stratified K-fold, for more robust evaluation, powerful hyperparameter tuning tools like grid search CV and randomized search CV to automatically search for the best model settings, and a whole battery of metrics, accuracy score, ROCA score, mean squared error, etc., to measure performance appropriately for different tasks.
So it helps you build and evaluate models properly.
Absolutely. And some algorithms can leverage parallelism through integration with a library called joblib. You'll often see an njobs parameter in estimators like random forest classifier or grid search CV, where setting njobs1 tells it to use all available CPU cores to speed up training or searching.
So efficient use of multi-core machines, too.
Where applicable, yes. Its overall architecture is widely praised for this clean, consistent, modular, and composable design.
And interoperability fits right into the ecosystem.
Perfectly. As we said, it's an integral part of the Python scientific computing stack, relying heavily on NumPy and SciPy for its data structures and underlying computations. It readily ingests data in various array-like formats, including NumPy arrays, SciPy sparse matrices, and, increasingly, Pandas data frames, though you often need to handle non-numeric columns explicitly first. It acts as that crucial glue between the data manipulation stage, Pandas, and the actual modeling.
Does it compete with deep learning libraries or complement them?
Definitely complements them. You often use Scikit-learn alongside TensorFlow or PyTorch. For instance, you might use Scikit-learn standard scalar or train-to-split to prepare your data before feeding it into a neural network. Or you might use Scikit-learn's grid search CV to tune hyperparameters of a deep learning model, perhaps using a wrapper library like Scorch, which makes PyTorch models look like Scikit-learn estimators.
So they work together?
Very often, yes. Scikit-learn's core dependencies are also deliberately minimal. Just NumPy, SciPy, and joblib, making it lightweight and easy to install almost anywhere. And critically, its API, estimator.fit.predict.transform, has become such a standard that it acts as a lingua franca for machine learning in Python. Many other ML libraries, even specialized ones like XGBoost or LightGBM, often provide Scikit-learn compatible wrappers, so they can be easily dropped into existing Scikit-learn pipelines and workflows.
So knowing Scikit-learn helps you use other ML tools too?
Definitely. It's like having universal remote for a huge range of ML tasks in Python.
Okay, so where is Scikit-learn most commonly used? What are its main domains?
It's incredibly widespread. A major use case is education and learning ML. It's probably the most widely used library for teaching machine learning concepts because its clarity and consistency allow students to focus on understanding the algorithms rather than getting bogged down in complex implementation details.
Great for teaching. What about practical use?
Absolutely essential for prototyping and experimentation. Data scientists use it constantly to quickly build and compare different baseline models on new datasets. Got a classification problem, you can try logistic regression, an SVM, a random forest, and gradient boosting in maybe an hour using Scikit-learn to get a quick sense of what works.
Rapid iteration. Is it used in production systems?
Yes, definitely. For production use for moderate scale ML. It's very common for tasks like customer churn prediction, spam filtering, fraud detection, predictive maintenance scenarios where the data volume fits on a single machine, inference speed is important, and often interpretability of classical models is a plus.
Oh, okay. Where else?
Research across many fields, bioinformatics, economics, social sciences, physics, where researchers need to apply standard ML techniques to their data. Its data pre-processing and pipeline utilities are often used even if the final model is something outside Scikit-learn, like a deep learning model or a custom algorithm. And many AutoML frameworks use Scikit-learn's components under the hood as building blocks.
And specific tasks.
It covers the main ML paradigms: classification, regression, clustering, dimensionality reduction like PCA, NMF, anomaly detection, and extensive tools for feature engineering and feature selection.
What is it not typically the first choice for?
As we discussed, it's generally not the go-to for problems involving raw, unstructured data where specialized architectures dominate. Think image recognition, where convolutional neural networks, CNNs, rule, natural language processing, where transformers are now state-of-the-art, or audio processing. While you could technically extract features from these and feed them into Scikit-learn, dedicated deep learning frameworks are usually far more effective for those domains. Scikit-learn's sweet spot is primarily tabular data or data that has already been processed into feature vectors. It's the classical ML Swiss Army knife.
Got it. So summarizing strengths, that consistent API is number one.
User-friendly, consistent API is absolutely a top strength. Makes it easy to learn and switch between algorithms. Comprehensive coverage of classic, well-established algorithms, it's got almost everything you need for standard ML tasks in one place. Reliability and performance are excellent due to the optimized C++ plus Python implementations. Famously well documented with tons of examples and user guides. A strong, active community. Its design actively encourages good ML practices like using pipelines and cross-validation, helping users avoid common mistakes. Provides robust metrics for evaluation and seamless integration with NumPy, SciPy, and the broader ecosystem. It's easy to save and load trained models. Truly a Swiss Army knife for classical ML.
Okay, and the limitations again, scalability is the big one.
Scalability is the main one. It's designed for single machine, in-memory computation. It doesn't natively handle distributed computing across clusters, so it hits limits with truly massive datasets. It's not for complex deep learning, no native GPU support, no tools for building intricate neural network architectures. While comprehensive, it may lack some cutting-edge specialized algorithms, although external libraries often provide Scikit-learn compatible interfaces. Its generalist nature means it might not be the absolute fastest option for all possible edge cases compared to highly specialized libraries, for example, for extremely high-dimensional sparse data. While improving, its built-in tools for model interpretability might be less extensive than dedicated interpretability libraries. And it generally requires the user to explicitly encode categorical variables into numeric formats before feeding them to most models.
But again, these limitations mostly define its scope, right?
Exactly. They're largely a result of its deliberate focus. It excels brilliantly within its chosen domain of classical ML on single machines, and it's designed to complement other specialized frameworks like deep learning libraries or the distributed computing platforms, rather than trying to be a universal solution for every conceivable ML problem.
Its real-world relevance must be huge then, despite the rise of deep learning.
Undeniably high. It's often the very first toolkit data science teams reach for when dealing with structured or tabular data. It's essential for rapid prototyping and widely used for building robust production models where data volumes are manageable or where classical models are preferred for speed or interpretability.
And it's open source and well supported.
Yes, it's open source permissive BSD license combined with strong community support and that NumPy sponsorship makes it a safe, reliable, and cost-effective choice for both businesses and researchers. In academia, it effectively democratized access to standard ML algorithms, empowering researchers across disciplines. It has profoundly influenced the culture of ML practice in Python, emphasizing rigorous validation and standardized workflows. Proficiency in Scikit-learn is almost universally expected in data science job postings.
Still essential even with all the hype around deep learning.
Absolutely, because a vast number of real-world business problems are perfectly well suited to the kinds of classical models Scikit-learn provides. Or Scikit-learn is used to establish strong baseline performance before attempting more complex deep learning approaches. Its layered role within the broader ecosystem, providing pre-processing, pipelines, evaluation, and robust classical models, remains absolutely crucial. It empowers practitioners everywhere to implement a huge range of ML workflows efficiently and reliably.
Wow. Okay, so as we bring this deep dive to a close, it's crystal clear that these 5 libraries, NumPy, Pandas, Matplotlib, Seaborn, and Scikit-learn, aren't just isolated tools. They truly form this powerful, incredibly synergistic system, a symphony, really.
That's a perfect word for it, a symphony. Each plays its distinct yet interconnected role, making the whole ecosystem far, far greater than the sum of its individual parts.
Yeah, you really see how they build on each other.
Absolutely. You can really think of it as this layered, composable architecture, like building with specialized Lego blocks that just click together perfectly.
Okay, so quick recap. NumPy.
NumPy provides that lightning-fast, efficient computational foundation, handling the raw numerical arrays and matrix operations with incredible speed. The bedrock.
Pandas.
Pandas builds right on top of NumPy, offering the high-level data structures, the data frame and series, with label axes, handling the messy realities of real-world tabular data, giving structure to the chaos. The data wrangler.
Matplotlib.
Matplotlib then acts as the core visualization engine. It provides the fundamental canvas and the granular artist-level control to create virtually any scientific plot you can imagine. The canvas.
Seaborn.
Seaborn, built directly on Matplotlib, serves as that convenient, high-level statistical plotting layer. It makes creating complex, informative, and aesthetically pleasing statistical visualizations much easier, often with just one line of code. The statistical art director.
And finally, Scikit-learn.
And Scikit-learn provides that uniform, consistent framework for applying a vast array of machine learning algorithms, classification, regression, clustering, plus the crucial tools for pre-processing, validation, and evaluation. The ML toolkit.
Their design philosophies just mesh so well, don't they? Leading to this robust, proven stack.
Incredibly complementary. Each library is truly essential because collectively they cover the entire typical data science workflow. You acquire and prepare your data using NumPy and Pandas. You explore, understand, and communicate insights from it using Matplotlib and Seaborn. And then you learn from the data, build models, and make predictions using Scikit-learn. It's a complete ecosystem.
And the fact that they're all open source, community-driven, and have evolved over years, yet their core ideas remain so relevant, that's pretty amazing.
It's a huge testament to the careful thought, the pragmatic design choices, and the user-centric development that went into each of them. It's largely because of this well-integrated stack that Python has become the dominant language for data science today. #outro.
And that brings us to the end of this deep dive. I think the key takeaway for you, our listener, is this. Understanding these libraries not just as code commands, but at this conceptual level, appreciating their why and how, their history, their strengths and limitations, it truly unlocks the full potential of Python for data science and ML.
Yeah, it lets you move beyond just writing code by rote and helps you really appreciate the sophistication happening behind the scenes. And, importantly, it helps you choose the right tool for the right job more effectively.
Definitely.
And maybe a final thought to connect this to the future. Consider the recent trend of integrating tools like Pandas with large language models, using libraries like Pandas AI or similar concepts. This hints at a possible future where some high-level data manipulation and analysis might become more conversational, less code-centric, at least for certain tasks.
You mean talking to your data?
In a sense, yeah. It raises an interesting question. What new kinds of insights might we uncover, or what new questions might we be able to ask our data when simply speaking to it becomes a more viable way to interact? And how might that reshape our relationship with these foundational libraries like Pandas? Will we still need to understand their nuts and bolts as deeply, or will they become even more powerful by becoming, in some ways, invisible?
Wow. That's a really fascinating thought to end on. Will the foundations become hidden infrastructure? Something to definitely mull over.
Food for thought.
Well, thank you for joining us on this deep dive into Python's powerhouse libraries. We hope you found it insightful. Until next time, keep digging deeper.